So welcome back to the second part of this module. Sabi nga natin dun sa last part nun, the kilogram was redefined, of course, along with other base SI units as ampere, Kelvin, and mole. So as we mentioned before, yung older definition niya was based on the prototype kilogram, which is an actual piece of metal stored somewhere, and the assumption was it wouldn't change in mass, but apparently it does shed some weight over time. So now they tried to make the kilogram become dependent on something constant. So they actually used a scientifically um, known constant, yung Planck constant natin, and they just basically had that equation, moved kilogram to one side and everything else on the other, and then used that number na as the definition. However, there's a slight problem with this, no? Kasi if you were to look at the Planck constant, meron din siyang kasamang iba pang base SI units such as the meter and the second. Although in this case, the meter and the second are defined in terms of the speed of light and delta VCS respectively. So this just means na yung kilogram now is based on the definition as well of the meter and the second. So again, here are the short definitions of the constants used as well as their numerical values. Again, I don't expect you to memorize these things, especially up to the last decimal place or digit, no? Pero just to give you an idea kung dapat maalaman nyo kung paano sila dinerive, ko ano yung idea behind them being used as the basis for defining the base SI units. So some geeky scientists find this as amazing na parang mayroong bagong kaganapan, no? Since we went from objects that are physically here and that change to concepts that will not change through time. So sa pagka-hardcore ni itong si Kuya ay nagpatato pa siya, no, sa kanyang kamay. And yung French wording doon, no? So yan yung for all times, for all peoples. So defining the meter is relatively easy, no? You just take the speed of light in vacuum, which is constant in meters per second, and then you isolate mo yung meter on one side, and then the value that you get is equal to the length of 1 meter. Or specifically, the 1 meter is the distance traveled by light in that fraction of a second. So as we know, the Kelvin or thermodynamic temperature is in a way a measure of the activity ng isang object, that something at molecules rather, or even atoms at 0 Kelvin will not move at all. So the Boltzmann constant, which is a relation of the energy of an object to its temperature, since constant siya, so yun na lang yung ginamit nila, no? Again, you put temperature on one side, then everything else set in to be able to define what 1 Kelvin is. Okay, and actually meron pang isa, pati yung Planck constant ay interrelated dito sa definition na ito. And basically that's how they define most of the other constants. They just, rather most of the other SI units, they just find a constant with a value that has been there and is not expected to change or be recalculated anytime soon, and then use that to define their base SI unit. Second, we get introduced to the concept of hyperfine transition frequency, which is just the frequency causes an electron to jump between low energy states. So it's a property of all atoms. So baka magtaka kayo, bakit naman cesium-133 atom yung napili? Okay, so two major considerations here is that because at that time, yung technology nila ay limited, so that yung ibang mga materials ay hindi nila kayang kunan ng hyperfine transition frequency. And at the same time, yung cesium, hindi sobrang dami ng isotopes niya, which would affect the calculations nito. Okay, so actually it could have been any atom technically, but it's a matter of how accurate we could get the measurements above all else and how easy it is to measure. So from high school, you may have remembered that the old definition of the mole is the number of atoms in 12 grams of carbon. But now, since they're moving towards using constants, they use the Avogadro constant or Avogadro's number to define the mole. So for the ampere, yung old definition niya kasi involves a hypothetical situation where you have parallel wires with negligible cross-sectional area and infinite length and so on. So medyo weird yun, kaya ayan, pinalitan lang nila. Now it's based on what the numerical value of the charge would be in coulombs or amperes per second when you use the delta V CS, which is a constant. So for candela, you measure the luminous efficacy of monochromatic radiation ng green light at 540 times 10 raised to 12 hertz. And that is known to be 683 lumens per watt, okay, which is actually equal to candela stereogens per watt, or base SI unit, candela stereogen per kilogram meter squared times second cube. Okay, so that is why you have other constants used to define it, kasi kung ano man yung pinang-define mo ng meter second at kilogram ay kailangan mo rin para ma-define yung candela. Steradian, by the way, or yung SR is a supplementary unit. So here are the two other SI supplementary units, yung plane angle, as you can see on the left, and the solid angle, which you can see in the right. So derived units are any combination of base SI units through algebraic means, so either by multiplication or division, as can seen below. Now, so any derived unit would be a function of just the 7 base SI plus perhaps any of the two supplementary units. As you can see in this table, like area is just meter squared, a volume is just meter cubed, and velocity is meters divided by time, or rather distance over time, and so on. So because there are so many derived units, one thing we must do is make sense of these derived units. Now, since we know the basic meaning of the 7 base SI and the supplementary units, then we could actually make sense in our minds what it means to combine them. Now, for example, if you have density as kilograms per cubic meter, then that means a substance with a volume of 1 cubic meter would have a weight of n number of kilograms. Or if, for example, you have a magnetic field strength, which is a linear thing, then for a certain length of maybe wire, you would have how many amperes of current, okay? So while we won't have to define every single derived unit textbook-wise, by simply looking at the numerator and denominator, we could make definitions for ourselves. So for example, if you have Newton, which is the unit of force, it's the force that gives to a mass of 1 kilogram an acceleration of 1 meter per second squared. So I hope that you take time in letting this concept sink in, kasi when we deal with things like power and energy, which are derived units, you want to be able to look at pag breakdown mo sila into the meters and seconds and kilograms, how do you make sense of it? Yun. So the next two slides are basically just a summary of the common derived SI units that you will use mostly for food engineering purposes. So take note that their names are in lowercase even if they are named after scientists. Pero pag naging symbol sila, usually they start with a capital letter. Okay, so please take note of that when writing down units, unless you're for some reason using it to start a sentence, they are always lowercase. Right, so meron din tayong tinatawag na mga dimensionless unit. So there are two types, no? Those are the ones na wala talagang dimensions, like specific gravity because the numerator and denominator cancel out. Okay. And there are those na even though meron silang dimensions na makukuha, hindi mo gagamitin yung dimensions na yon. Like for example, the body mass index, which is para malaman mo kung overweight ka or obese or underweight, etc., is defined by weight in kilograms divided by height in meters squared. But no one represents the BMI in kilogram per meter squared. Alright? Kasi hindi siya useful. Alright? Kasi ang kilogram per meter squared, tingnan mo, is para siyang force without the acceleration, mass over area, mass per unit area. Pero kung titingnan mo in reality yung purpose niya, ang ibig sabihin niyan, yung isang tao na may ganitong bigat ay tatayo sa isang square na ang length at width ay equal sa kanyang height. But that doesn't make any sense. Okay, so for the sake of modeling, BMI is just telling us that this number more or less represents your health status, weight to height ratio. Okay. There are other numbers like for example the Nusselt or Reynolds numbers. So if you look at them, meron mga dimensions kasi yung sa numerator and denominator nila. But when you're computing for them, you present them just as a number without any units of measurement because they're used for modeling phenomena. Okay, Reynolds number ma-encounter natin yan sa fluid flow because Reynolds number is just something you compute from, let's say, a fluid system, water flowing in a pipe or liquid flowing in a pipe, and then based on the viscosity, the pipe diameter, and the flow rate, the speed of the liquid passing through, you calculate the Reynolds number, and that number could be used to say whether the flow is turbulent or not. Okay, so these are some conversion exercises that you could do. The first two have solutions after this slide. No? It's important to note, of course, that unit conversion is something that we could apply in all areas of life, whether it be food or non-food. And magandang maisip natin na kahit sa mga bagay na walang kinalaman sa pagkain ay pwede natin itong magamit para ma-practice natin siya in real life situations. So that's why some of the things I included there are mga common objects na wala namang kinalaman sa food science. So you can do this on your own free time. Since conversion is all about practice, no, I know hindi ko na kailangan ituro yung skill sa inyo dahil ginagamit niyo na ito mula high school pa. But at least this is something that I could force you to try and solve certain problems for you to develop that skill along the way.